Hi everyone, welcome back to our YouTube channel. So in today's video, we will looking at uh, these questions from checks.com. So the normal distribution question, and this question is all about using multivariable calculus to solve and simplify the problem. So without wasting much of our time, uh, let's go straight to the question. As you can see, the question already been posted. The A section now, we are asked to sketch the graph. We're asked to sketch a graph in this A section. So we're asked to sketch the graph of quarter disk D1, D2, and a square S. So we are given the equations for these regions. So we are asked to sketch them and observe the relationship between D1, S, and D2. So here I will recommend we use Desmos software to for this sketching section. So Desmos is a very good software, it's a very good app for graphing. It's a good graphing tool. So just let's search online for Desmos. So if we have the application on our mobile, let's click on it, then be able to plot this problem on Desmos. So now we are required to sketch the following region. So the for the first quarter disk, that is the D1, we are given the equation that is the quarter circle with radius of A centered at the origin, the first quadrant. So we are also given the boundary. The boundary is a quarter of the circle, which is a x squared plus y squared is equals to a square. And as well for the D2, which is also a quarter circle, but this time around is with radius root a2 root a2. So center is centered at the origin as well, also in the first quadrant, and the boundary is a quarter of the circle. Is the boundary is a quarter of the circle. X squared plus y squared is equals to 2a squared. Then the last region we are given, that is x. Yes, this is a square in the first quadrant with side length of a. So to plot this, all we just need to plot this, we need to plot this on our Desmos app. Then Desmos will do the rest. We insert this equation, Desmos will do the plotting for us. As we can see, it's the same Desmos we use to grab this region. So as you can see, the one showing this is the result of the sketch region. The red circle is our D1, and the blue circle is our D2. We can recognize our S, which is the square, that is the green line. So as you can observe, just like we were given in the question, we should observe that D1 lies inside S. That is, our first quarter disk lies inside our square. So as we can see, the first quarter of our D1, that is the circle, lies inside our square, because it lies because the radius, that is the side length of the square, is bigger than the radius of the circle, that is the circle D1. Then you can see that that same square now lies inside D2. That is, the square is inside of the D2, the blue circle. So as you can see, the red is D1, the blue circle is D2, and our green line is the square. So that's it for the A section. That is for the A section. So they say we should observe. We're able to see that because technically and mathematically, D1 is a subset of S and S is a subset of D2. That is why this relationship is possible. That is, D1 lies in S and S lies in D2. So without wasting much of our time, let's go to the B part. B now say we should consider the function f of x comma y is equals to exponential of bracket minus x square minus y square close bracket over 2. By changing to polar coordinates, show that double integral over the region D1 f of x and y dA is equals to pi over 2 open bracket 1 minus exponential minus a square over 2, and we should also show that double integral d2 f of x y dA is equals to pi over 2 1 minus a square. So now all we want to do in this B section, we are doing two things. First one is we are showing that the double integral of d1 f x of y dA is equals to pi over 2 1 minus a square over 2. We are trying to show this and this as well for D2. We are trying to show this. So we are asked to convert to polar coordinates to be able to show this. So where x y is exponential x squared y squared over 2. So now to solve this, we'll be taking the first region first, which is the D1, the first quarter disk. So convert it to polar. What is the polar coordinates? We have x is equal to r cos theta, y is equal to r sin theta, then our dA, which is dr d theta. So with this now, and by convert it to polar form, we have this to be in this form now, which is by conversion, we want it to polar, and r square over 2. So exponential minus r square over 2. You might be thinking, how did I end up getting this exponential minus r square over 2? Just from this substitution of polar coordinates. X is equal to r cos theta. When you insert our new value of x and y in terms of r and theta into this x and y, we will get minus r square over 2. Now you might be thinking, we have cos, we have sin. How do we end up with only r square? So this is our first trigonometry identity, that is sin square theta plus cos square theta is going to give us 1. So that was how we're able to have minus r square over 2. So without wasting much of our time, so now for D1 now, for D1 we have, given our range to be this, pi over 2. So now D1, this becomes f y dA becomes pi over 2 p r square over 2 r dr d theta. So now this is what we'll be solving. We'll be solving this double integral now. So that's what we'll be solving to prove that it's going to give us this. So let's continue solving. Let me adjust this for better view. So let's continue solving. So now with this, all we just need to do is take this one by one and integrate it. So let's take the simplest part, which is 0 pi over 2 the theta, and this is just 1. So this will give us theta. Then we insert our our limit. So we are going to be having pi over 2 minus 0, which is pi over 2. This gives us pi over 2 here. Then for the second integral, to a dr. So this, solving this by substitution method, that is, how you just, so let's say let u equals r square over 2. Then we differentiate r square over 2, which is 2r over 2. 2 cancel 2, which is r. Then inputting everything, r will cancel r. We are left with e raised to power minus u. So that will give us this as our final answer, minus e r square over 2 is starting our limit. So starting our limit now. So this will give us 1 minus a square over 2. So this is for this, then this is for this integral. Then we combine the results as well. So we multiply them, that is, draw this, let's combine the result. 0 pi over 2, 0 a dr. The theta is going to be pi over 2 times 1 minus a square over 2, which is pi over 2, 1 minus a square over 2, which we have just proven as required. Pi over 2, open bracket, 1 minus exponential a square over 2. So we have just proven this for the first region, that is for our D1. So now we are going to do the same process for our D2. So for our D2 now, for our D2, D2 is it the region given and everything. Our D2 will be root pi root 2 the theta, which is the same thing, 2 pi here, the theta, which is pi over 2, then our second integral, which is square over 2 r dr, which will give us the same thing as the first one. Then inserting our limit of this, which will give us 1 minus a square. So now for this, combining them, we have this to be pi over 2 1 minus a square, just as we want it to be, just as we want it to be, just as required for us to prove. So this is B. We have successfully solved for our B. We have shown that this function, integrating this function over the region D1 and D2 is going to give us pi over 2 times 1 minus exponential e exponential minus a square over 2 and double integral d2 fxyd is going to give us pi over 2 times 1 minus exponential minus a square. So we have just solved that for our B. Now going to our C, show that our C says we have to, for the square now, show that f sub y dA equals to a minus s square over 2 dx square. This is what we are asked to show. We are asked to show that this is a square. This, for the square region, we are asked to show that integral from 0 to a exponential minus x square over 2 dx square. We are asked to show this. So now this, we can solve this as this. We can break it down as s as integral from region x dA. Since this is square, you can repeat it, make it like this, write it in this form. Then working our way around this, we have something like this, minus pi square over 2 dy dx dx. So let's simplify this right hand side. Which is also split it as this. So if you see this exponential minus x square over 2 with the limit inserted, as is from 0 to a, for exponential minus y square over 2 and the same limit, you see that they are both the same function. Just the difference is the x and y, and they both have the same limit. So it's going to give us the same final answer, whatever that answer is. So we can as well say it is same equals to y square over 2 dy. Hence they are both the same thing. Hence du equals a x square over 2 dx square. So that's it for our C part. That's it for our C part. Now coming back to our section D, we are asked to explain why pi over 2 bracket 1 minus exponential minus a square over 2 close bracket is less or equal to the integral of its limit from 0 to a exponential minus x square over 2 dx all into square. Then and this integral is also less than or equal to pi over 2 1 minus exponential minus a square. So we are asked to explain why this inequality is like this. So this inequality holds because this holds because D1 is a subset of S, and S is a subset of D2. So this is our D1, this is our S, then this is our D2. So that's why this will hold. As you can see from our section A in our graph, the graph we did earlier, we saw that D1 lies in S and S lies in D2. So whatever D1 is, it can be found in S, and whatever S is, it can be found in D2. They are all subsets of D2. So D1 is a subset of S, S is a subset of D2. And integrals over smaller regions yield smaller results. So that's it for our section D, our D part. Now into the E part. You say we should use D, we should use our answer in D. We should use our answer is D to show that is you A and this is equals to pi over 2. So we should solve for this integral. We should hence solve and show that this is equals to pi over 2. This is very straightforward right from our illustration in D. And we know that in D now, from D, all we just need to do is, sorry, I think this is infinity, not a infinity. So now from our answer in D now, all we just need to take a limit as a tends to infinity. So limit as a tends to infinity of pi over 2 1 minus a square over 2. So when we take this limit as a tends to infinity, this exponential power infinity negative infinity, this will give us 0. So we are going to have 1 minus 0, which is 1, then pi over 2 times 1, which is pi over 2. Then for this as well, for the integral itself, from our D now, over 2 dx, you can put everything in square. This will give us infinity put everything in square as well. Then for the D2 region now, infinity pi over 2 1 minus a 2. Same thing as a tends to infinity, exponential as a tends to infinity. So this will give us 0, 1 minus 0, which is 1, pi over 2. So now with this limit inserted and with the condition that we are given in D, that we're able to derive that D1 is a subset of S and S, that is square, is a subset of D2. So we are saying pi over 2 this pi over 2 is less or equals to this integral square, and we're saying this integral square is less or equals to this pi over 2, and they are both the region below and above this s, that is the square region, is pi over 2. So definitely, that is what I'm saying in this is this. So definitely, hence square over 2 dx. Now this will give us pi over 2, that is the square, give us pi over 2. So that is it for our e. That is it for our e now. So I believe the question is the integral from 0 to infinity exponential minus x square over 2 dx without the square. Now all we're going to do is take the square root of that. So we have this, it becomes square over 2 dx, which is the square root of this pi over 2, which is root 2 pi over 2. That's our final answer. So that's it. So we are putting our final answer to that. So now to the last one, which is our e, our f. I'm writing this. Yeah, this is now 2 pi over 2. So now our f. Our f now, we are asked to find this from minus infinity to infinity. A square over 2, 2 pi dx. So to solve this, we are going to be straightforward here. We are going to normalize it by normalization. At least this is standard normal distribution. So and this 2 over 2 pi is a constant. Let's bring it outside. 2 pi infinity to infinity minus a square over 2 dx. Now to solve this, we are going to be applying what we did in section B, that is converting it into polar coordinates. So when we convert this into polar coordinates, following the same steps as we did in section B, we are going to have something like this at the end of the day. I'm going to have 2 pi times root 2 pi, so which give us 1. So hence square over 2 2 pi giving us 1. So this brings us to the end of today's lesson. Don't worry if you are getting this section F confused as it's fast. Don't worry. Look forward to our next video. In our next video, I'll be breaking this section F down more and more for us. So we'll be solving similar question in our next video. We are going to be applying this polar coordinate to solve something like this problem. So don't get confused. Just look forward. Please subscribe and look forward to our next video. Thank you very much. So